If we add 1 tablespoon of sugar into a cup of water at room temperature, how much of it can be dissolved? If we add a coagulant to improve the solubility of fine particles for water treatment, what would be the highest concentration of this coagulant in mass concentration unit, such as milligrams per liter? In civil engineering, particularly in water and wastewater treatment engineering, calculations related to solubility are frequently needed in practice. In today's video, we are going to talk about the aqueous solubility of metal salts. The solubility product constant, Ksp, is an equilibrium constant measuring the extent to which a sparingly soluble ionic compound dissolves in water at a given temperature. It is calculated by multiplying the molar concentration of ions raised to the power of their stoichiometric coefficient. Although the solubility product constant represents the maximum product of ion concentrations in a saturated solution, it does not reflect the maximum concentration of the dissolved salt in this saturated solution. For this purpose, the concept of solubility is introduced. Let's create a table to show the mass shift from solid phase to the liquid phase. Before the dissolution starts, we have m moles of solid salt to be added to 1 liter of water. No ions exist yet because the dissolution hasn't started yet. After the solid salt is added to the water, until equilibrium is reached, S moles of this solid salt is dissolved, marked by a negative change for this reactant. At the same time, according to the stoichiometry of the dissolution reaction, Ms moles of the cation ions are produced and Ns moles of the anions are produced. Now we can substitute these molar concentrations into the equation of the solubility product constant, Ksp. You can pause the video at this time to see how the basic rearrangement helps us to evolve this equation into its final form. Ksp equals to m raised to the power of m, n raised to the power of n, multiplied by s raised to the power of the sum of m and n. With Ksp on the left side and s on the other side, we can rearrange this equation to express s using Ksp, which is the equation we have in this slide. Because in the setup of this derivation, we have S moles of salts dissolved in 1 liter of water, the unit here for S will be molars per liter. To convert the molar concentration in molars per liter into mass concentration in grams per liter, we'll multiply the molar concentration by the molecular weight, mW, of the salt. If the final concentration should be the other mass concentration unit, such as milligrams per liter, we just need to work on the unit conversion afterward. Now, let's take a look at one example of solubility calculation. At 25 degrees Celsius, the solubility product of lead fluoride, PbF₂, is Ksp equals 3.6 times 10 raised to the power of -8. Assuming pure water and ideal behavior, determine the solubility of lead fluoride in milligrams per liter. Atomic weights are given. Now, to determine the solubility of lead fluoride, we'll record the last equation we derived, noting that the resulting units of S would be in grams per liter with this equation. To determine the values of M and N, let's take a look at the dissolution reaction of lead fluoride. So 1 mole of lead fluoride will dissolve into 1 mole of lead ion and 2 moles of fluoride ions. Hence, m equals 1 and n equals 2. Besides, we also need to know the molecular weight of lead fluoride. Since we are provided with the atomic weights of lead and fluoride, we can easily find out the molecular weight of this salt, 245.2 grams per mole. And finally, we can substitute the values of m, n, and molecular weight, as well as the Ksp values into the equation. And we find that the solubility of lead fluoride at 25 degrees Celsius is 0.510 grams per liter, and that is 510 milligrams per liter. If you want more videos like this, focus on how engineers actually think on exams under time pressure, remember to like this video, subscribe to the channel, and leave a comment with the next topic you'd like me to cover. Your engagement is my biggest motivation. I'll see you in the next one.